Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, control theory, machine learning, optimization, mechatronics, robotics, etc. In this video tutorial you will learn how to implement a model predictive control algorithm in C++ by using the Eigen matrix library. You will learn how to implement the model predictive control algorithm from scratch. Moreover, you will learn how to implement this algorithm in a disciplined and object-oriented manner. You will learn how to write a C++ class that implements the model predictive controller. Here is the C++ class. This class embeds the solution and it contains several functions that are used to compute the solution and to simulate the system dynamics. Furthermore, this class contains a function that's used to save the simulation data to an external file. Then you will learn how to write a driver code file for using the class. This driver code sets up the problem, defines the dynamical system, and it computes the solution. Before I start with the explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 300 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. To make this video tutorial self-contained, first we will quickly go over the basics of the model predictive control method. We will not dedicate a lot of time to derivations of the algorithm, mainly because I created a separate tutorial that explains how to derive a model predictive control algorithm from scratch and how to implement this algorithm in Python. This tutorial can be found by clicking on this link. And here's the tutorial. I will also post the link to this tutorial in the description below the tutorial that you're currently watching. Also, I will post a link to the GitHub page with all the C++ codes explained in this video tutorial. The link will also be given in the description below this tutorial. We consider the linear system given by the equation number 1. Over here, xk is the state, k is a discrete time instant, uk is a discrete time control input, a, b, and c are the system matrices, and zk is the output that we want to control. Here it's very important to keep in mind that zk is not necessarily the observed output. That is, it's not necessarily equal to the measured output. In our problem formulation, zk is actually a set of state variables that should follow a desired reference trajectory. In our problem formulation, we assume that the state of the system is perfectly known. And in my future video tutorials, I will relax this assumption. That is, I will use a state observer to estimate the state. This figure illustrates the main idea of the model predictive control algorithm. First, we need to explain the prediction horizon. The prediction horizon is the future horizon over which we will predict the state trajectory. That is, we are currently at the time instant k and we want to predict the state trajectory, that is this blue line, and we want to do it over certain prediction horizon in the future. The length of the prediction horizon is denoted by f. Then, having this prediction, that is, having the prediction of the system state or controlled output, our goal is to control the system over this future prediction horizon. That is, we want to compute a set of control inputs that will steer the system's state or output trajectories to the desired trajectory. Now, we need to explain the control horizon. The control horizon is the future horizon over which we actually change the control inputs. That is, we assume that the control inputs are changed from here until the end of the control horizon, and after the control horizon is completed, we assume that the control inputs are constant and they are equal to the last control input in the control horizon. Both prediction horizon and control horizons, or better to say their lengths, can be seen as the tuning parameters of the model predictive control algorithms. They can even be equal to each other. Next, we need to introduce a proper notation. When you see a control input written like this, you should interpret this notation like this. Let's write it down again. U, and then in the subscript, you will have something like this. K plus I, vertical bar, K. This is the control input at the time step K plus I, and that is computed at the time step K. This control input is determined as the solution of the model predictive control problem. Similarly, if you see states written like this, and let's repeat the notation, X, and then in the subscript, K plus I, vertical bar K, this is the prediction of the state vector at the time instant K plus I, and that is computed at the time instant K. Similarly, when you see Z, K plus I, vertical bar K, this is the prediction of the output vector at the time instant K plus I, and that is computed at the time instant K. The goal of the model predictive controller is to determine a set of control inputs UK plus I vertical bar K over the interval I goes from 0 until the end of the control horizon, and this input should be computed at the time instant K such that the output of the system zk plus I follows prescribed output trajectory or desired control trajectory. This is done by using the knowledge of the current state, xk, and the system model matrices A, B, and C to predict the output trajectory, and then to minimize the difference between the desired and predicted trajectories. The first step in developing a model predictive control algorithm is to develop equations for predicting the state and the outputs. Let us assume that we are currently at the time instant k and that we want to make state and output predictions up to the future time instant k plus f, where f is the length of the prediction horizon. From the state and output equations, we can obtain these two equations given by the equation number 2. These two equations predict the state and the outputs at the time instant k plus 1. Then, we can write a similar set of equations for the time instant k plus 2, and these two equations are given by the equation 3. These equations predict the state and the output at the time instant k plus 2. By using the same principle for the time instant k plus 3, we can write equations 4. The last equation in equation 4 can be written in the compact form given by the equation number 5. By continuing with this procedure until the time index v, and v is the control horizon, we obtain the equation number 6. In equation number 6, this vector is unknown. This vector represents a sequence of control inputs that should be applied to the system. The index v is important mainly because after this index we have this equation, and this is a constraint on our model predictive controller. We simply assume that all the inputs after the time instant k plus v minus 1 are constant, and they are actually equal to the input at the time instant k plus v minus 1. That is, all the inputs after the control horizon are equal to the last input in the control horizon. By using this equation, we have for the time index k plus v plus 1 this equation, and notice the difference. By using the same procedure and by shifting the time index, we obtain this equation, and I will zoom out such that you can see it very nicely. Here it is, where this matrix over here is defined like this. In the general case, we can introduce this notation to simplify further equations. by combining everything together, that is, all the equations starting from this equation until our last equation, that is until 10, we obtain a lifted system description given by the equation number 13. Let us give a physical interpretation of this equation. We know the state vector xk. If we would know the input vectors, that is, these vectors grouped in this lifted vector, we would be able to predict the output of the system starting from k plus 1 until k plus f. That is, we will be able to predict the outputs of the system during the prediction horizon. This equation serves as the basis for developing the model predictive control algorithm, and this equation can be written compactly as equation 14, where the lifted system matrices O and M are defined over here. Here is O and here is M, and here are the vectors U underline and Z underline. The model predictive control problem can be formulated as follows. The goal is to track a reference output trajectory. Let these desired outputs be denoted like this. What do we see over here? Z, k plus 1, d is the desired output at the time instant k plus 1. Z, k plus 2, d is the desired output at the time instant k plus 2, etc. When you see a superscript d, this means that the outputs are desired outputs. These vectors can be grouped together and we can form this lifted vector zd. A natural way of formulating the model predictive control problem is to determine the vector of control inputs u such that this cost function is minimized. So what do we do over here? We take our desired output and we want to make our true output of the system to be as close as possible to desired output. This is nothing less than a least squares problem. And we can solve this least squares problem relatively easily. However, there is one big issue. The issue with this approach is that we don't have control on the magnitude of control inputs u. The control inputs can be extremely large and impossible to be applied in practice, or they can lead to actuator saturation that can lead to devastating effects in a feedback control loop. Consequently, we need to introduce a penalty on the control inputs in the cost function. Furthermore, we need to introduce weights in this cost function to have better control of the convergence of the algorithm. To penalize the control inputs, we introduce this cost function. This first part of the cost function penalizes the magnitude of the first control input that we apply to our system. And this control input is the most important one, mainly because we will directly apply it to the system and we will neglect all other control inputs. The second part of the cost function starts from here and ends here. This second part penalizes the difference between two subsequent control inputs. In that way, we limit the change of control inputs from one step to another. The matrices Q0, Q1, Q2 until QV-1 are the weighting matrices that are selected by the user. That is, we can tune the algorithm by properly choosing these matrices. We can write this cost function in a more compact form. First, we introduce this equation. That is, we introduce this matrix. By multiplying this matrix and this vector, we obtain this vector. And you can see that the entries of this vector actually appear over here, over here, over here, etc. This expression can be written like this, where the matrix W1 is defined like this. Then, by using this new notation, this cost function can be written like this, where the matrix W2 is a block diagonal matrix and all the Q matrices, that is, all these weights, are on the main diagonal of this matrix. Next, we introduce a part of the cost function that corresponds to the tracking error. This cost function is defined like this. Again, to remind you, zk plus 1d is the desired output, and zk plus 1 vertical bar k is the predicted output. Now, we can introduce this block matrix where P1, P2 until Pf are again symmetric weighting matrices, and they are determined by the user. By using all these equations, we can write this cost function like this. If we now substitute the expression for z from this equation in our expression for the cost function, that is over here, we will obtain this equation. And then we can introduce this notation. S vector is z desired minus O times xk. And since we know zd, we know O, and we know xk, we perfectly know this vector. And consequently, our cost function can be written like this. This part of the cost function penalizes the difference between the desired trajectory and the control trajectory. Next, we introduce the global cost function given by the equation 29. This global cost function is the combination of the cost function penalizing the tracking performance, that is, penalizing the tracking error, this part, and this part over here penalizing the magnitude of the first control input and penalizing the difference between subsequent control inputs. By substituting this equation in this cost function, we finally obtain this expression. We can expand this cost function like this. Next, we need to minimize this cost function with respect to u. To do that, we need to consult this nice reference. So I will click over here and I will go to the chapter 2.4. In that chapter, you can find the expressions for derivative of matrices, vectors, and scalar functions. We will only need two equations. They are given like this. If A and H are constant vector and constant matrix, that is, A is a vector and H is a matrix, then if you compute the derivatives of these two expressions with respect to some vector W, we will obtain A, and over here we will obtain 2h times w. Then, by using these two equations, we can differentiate all of these terms. And here are the results. For example, the derivative of the first term over here is 0. This is because this expression doesn't depend on u. On the other hand, the derivative of this expression with respect to u is given over here, etc. By using these formulas, we can actually compute the partial derivative of j with respect to u. Again, here is j, and here are the partial derivatives. To find the minimum of this cost function with respect to u, we set this expression to 0. From the resulting expression, we obtain this equation, and finally we obtain this equation. From the last equation, we obtain the solution of the model predictive control problem. It's given like this. What do? We take this matrix, we compute this matrix, and we simply invert this matrix. Of course, in practice, there are more fancier ways that avoid inversion of matrices. However, for simplicity, I'm not going to go in that direction. In my code, I will simply invert this matrix, and you can later on optimize the code if you want. The solution of the model predictive control problem, that is the vector u hat, can be represented like this. We only need the first entry, that is, we only need this vector uk vertical bar k. We apply this input to our system, and we then wait for the time instant k plus 1. At the time instant k plus 1, we observe the state xk plus 1, and we form another cost function for the time instant k plus 1. And we compute its solution, and we apply uk plus 1 vertical bar k plus 1. To illustrate that, the solution at the time instant k plus 1 will look like this. The u vector will have these terms: u k plus 1, then u k plus 2, k plus 1, up to u k plus v k plus 1. Then again, we only need this part. We apply this part to our system, and then we proceed to the time instant k plus 2, and we repeat the complete procedure. Let us summarize the algorithm once more. At the time instant k, on the basis of the known state vector xk and the system matrices A, B, and C, we form the lifted system matrices and we compute the solution u hat given by this equation. What do we do next? Then we extract this first entry of the solution and we apply it to the system. Then we wait for the system to respond and we obtain the measurement xk plus 1. We shift the index to xk plus 1 and we go to step number 1. Now again, in step number 1, the time instant is k plus 1. We again form the cost function, we do all the procedure, lift the matrices, and we compute a new state vector, new control input vector. However, over here we will have k plus 1, and then we apply it to the system. And we recursively repeat this procedure. To test the model predictive control algorithm, we use a mass spring damper system shown over here. We have two masses, M1 and M2, that are connected by springs and dampers. We assume that the following parameters are given: masses M1 and M2, spring constants K1 and K2, and damping constants D1 and D2. In my previous tutorial, whose link is given over here, I derive a state space model of such a system. The derivation is given over here, and you can go over this derivation. I will not do that in this video tutorial in the interest of clarity and brevity. Here's the state space model. Or you can also see it over here. The states are the position of the first mass, that's denoted by x1, the velocity of the first mass, denoted by x2, the position of the second mass, denoted by x3, and the velocity of the second mass, denoted by x4. The control input is the force F. Here it is. And here are the system matrices, AC, BC, and C. However, there is one issue with this state space model. The matrices AC, BC, and C are in the continuous time domain. However, our model predictive control algorithm was developed under the assumption that the system is given in the discrete time. Consequently, we need to discretize the state space model. To discretize the state space model, we use the backward Euler method. We simply approximate the first derivative of the state vector x by using the backward finite difference. And here's the result. We can rearrange this equation and we can obtain the equation 47, where the system matrices A and B are now in discrete time domain and they are defined like this. The output equation remains the same. If we simulate the state space model, that is, if we apply a constant input uk or a constant force to this mass m2, we will obtain such a response. We can see that the system is underdamped, and I deliberately selected such a system in order to make the control problem more challenging. That is, I want to test my model predictive control algorithm on a challenging case. Next, we will explain how to implement the model predictive control algorithm in C++. For that purpose, you need to visit a GitHub page dedicated to the implementation. Here's the link to the GitHub page. I will post this link in the description below this video tutorial. Next, you need to download these files. To do that, you will click over here and you will download the complete zip file. Save it, for example, in your Downloads folder. Then visit your Downloads folder, open the file, and extract them to a new folder. Over here, under this folder codes, I will make a new folder called MPC test, and I will extract or copy and paste files over here. Here they are. The next step is to compile these C++ files. I will explain how to compile these files by using the VS Code editor and the Microsoft Visual Studio C++ compiler. However, you don't need to follow this path. Of course, you can also use any other C++ compiler. If you are completely new to C++ and the VS Code editor, don't worry. I created separate tutorials that explain how to install the VS Code editor and the C++ compiler. Also, I created a tutorial that explains how to install the Eigen C++ matrix library in the VS Code editor. Links to these tutorials are given in the description below this video tutorial. Okay, let's start. Click on Start and type Developer. If you have properly installed the Microsoft Visual Studio and the Microsoft Visual Studio C++ compiler, you will see this command prompt. Click on it. Next, you need to navigate to this folder. Let's do that. cd codes, cd MPC, test. Here it is. And here are the files. The next step is to start the VS Code editor. To do that, type code and type dot. And here we are. And here are all the files. Perfect. In order to successfully compile and build these C++ files, we will have to do a few adjustments in the VS Code editor, and we will also have to install the Eigen C++ matrix library. The best way for making these adjustments is to try to compile the driver code. To compile the driver code, locate the driver code C++ file, and over here you need to compile the file. However, before doing that, you need to select the proper compiler. I will select this compiler, cl.executable, and this is the Microsoft Visual C++ compiler. And of course, you will see a few errors here. However, ignore these errors. So, what did we achieve with this? We actually generated this folder, and in this folder we generated this file called tasks.json. Over here in this file we need to adjust several parameters of our compiler. Since we are using the Eigen C++ matrix library to perform matrix calculations, we need to tell to our compiler the location of this library. To do that, we need to locate the library on our computer. Let's find the library. In my case, the library is located over here, under the folder Toolbox Eigen 3.4.0. I will simply copy and paste this path over here, and I will make a few adjustments. First, you will need comma over here, then type this dash, capital I, and copy and paste the path. However, you will have to make a few adjustments. The path should look like this, so change the symbols, and over here you will need this part. Save this file. Besides making the adjustments to this file, we will have to make adjustments to another file. That is, we will need the properties file. To generate the properties files, press Ctrl, hold Shift, and press P, and click over here. And immediately you will see the properties file. Again, what did I do? Control, holding Control, press Shift, hold Shift, press P. And over here you will click on this option and you will see immediately the properties file. Over here, under the include path, we need to generate the path. Consequently, I will type comma, and in the new row, I will add the path. Again, change these values, You don't need -i at the beginning, and this should be the path. After creating these two files and after creating a few adjustments, we will be able to compile our driver code. Let's do that. Click on the driver code, and over here, click on Run C++ file, and let's see the output. So something is happening over here, and voila, here's the output. MPC simulation completed and data saved. You will immediately see these comma-separated value files, and I will explain them later on. As I mentioned at the beginning of this video tutorial, we will be using the object-oriented approach to implement the model predictive control algorithm. Consequently, I wrote a class that implements the control algorithm. Here is the header file of our controller. Let's open this header file. That is the header file of our class. First, we include string, and then we include Eigen dense. Eigen dense header file is necessary since we will be performing matrix operations. Then we are using namespace Eigen. Don't forget this line, otherwise you will not be able to use the Eigen library, and we are using the namespace std. Here is the default constructor. I didn't change it. It will be an empty function. Here is the constructor that I will be using. The input arguments of our constructor are A input, B input, and C input. These are the A, B, and C system matrices. Then the prediction horizon is denoted by F input. The control horizon is denoted by V input. Then the weighting matrices W3 and W4 are denoted by W3 input and W4 input. The initial state is denoted by x0 input, and our desired trajectory is denoted by desired control trajectory total input. This constructor will initialize all the private variables, and it will construct the lifted system matrices O and M, as well as the control gain matrix necessary to compute the control inputs. This function is used to propagate the dynamics and to compute the MPC control solution. This function is used to save the data in comma-separated value files. Here they are. We will specify the name of the file that will store the desired control trajectory, inputs, states, outputs, and lifted system matrices. We will be using these comma-separated value files to visualize the results. To visualize the result, we will actually use a Python code file that's shown over here. Later on, I will explain the Python code file. Let's look into the private member variables. This variable is used to track the current time step k of the controller. That is, k is the discrete time index. To remind you, the dynamics looks like this. xk plus 1 is axk plus buk. And this k is actually this k in this equation. Then, over here, we need to store m, n, and r. M is the input dimension, n is the state dimension, and r is the output dimension. Over here, we store our system matrices, weighting matrices, initial state, total desired trajectory, prediction horizon, and control horizon. Then we will need several other variables. As I mentioned previously, I will visualize the results in Python, and consequently I need to export the results, and I need to track all the variables. This matrix will store the computed state trajectory. This matrix will store the computed inputs. This matrix will store the outputs, that is, the controlled outputs. These two matrices, O and M, will store the lifted system matrices. To remind you, our prediction equation looks like this. Z is equal to O times xk plus M times U. And these matrices, O and M, are actually the matrices defined over here. And finally, we will store our gain matrix. To remind you, The computed solution is defined like this. And this part over here is actually the gain matrix. The constructor will actually construct this gain matrix. Next, let us open the class implementation file. You need to click on this file. We include input-output stream, tuples, strings, fstream, vector, Eigen dense, and of course we need to include the header file. We are using the namespaces Eigen and std. Here is the implementation of the default constructor. We are not doing anything. Here is the implementation of our constructor. This constructor will initialize all the private member variables, and it will construct the lifted system matrices O and M as well as the control gain matrix necessary to compute the control inputs. Let's look into this constructor. Let's see what's happening over here. We assign A is equal to A input, B is equal to B input, and C is equal to C input. Also, we make assignments for other member variables. That is, we take these inputs and we store them as private variables. Then, we extract the M, N, and R system dimensions, and we do that by calling these functions rows and columns of the eigendense matrix library. We simply type a.rows if we want to extract the number of rows of the matrix A. We initialize the variable k that will track the current time instant. Then we extract a part of the trajectory that's used for control. Next, we need to initialize the matrices that will be used to store the state trajectory, the input trajectory, the output trajectory. Also, we need to initialize the matrices that will be used to store the O-lifted matrix. Over here we do that, and over here we construct our lifted O matrix. Here's the mathematical definition of the lifted O matrix, and here's how we construct this matrix by using the Eigen C++ matrix library. We simply construct this matrix one block row at a time. That is, we construct CA, CA squared, CA to the power 3 until CA to the power F, and we recursively compute these matrix powers, as you can see over here. Here's how we select the block rows of the O matrix, and we simply assign the corresponding powers of A multiplied by C. Next, we need to initialize and define our lifted M matrix. Here's the M matrix. Since there are two patterns for forming this matrix, we need to construct this matrix in two steps. We can see that one pattern of blocks is from the beginning until here, and another pattern is from here to here. The limit is actually the control horizon denoted by V. So we iterate block by block starting from 0 until V minus 1. This block is V minus 1. And then we continue from V block until the block F. In C++, we construct this matrix like this. Over here, we iterate until the control horizon, and we form these blocks by following the pattern. After that, that is, from the control horizon until the prediction horizon, we form the other blocks. Here's how we do that. For j is equal to 0, j is the column index, and for other values, for j from 1 until the dimension of the matrix, that is, until the columns of the matrix, we follow a different pattern. Once we form the lifted matrices O and M, we can construct the control gain matrix. The control gain matrix is defined by this equation, and here's how we define this matrix by using the Eigen C++ matrix library. Over here you can see the gain matrix, and this part over here is actually defined over here, and the final gain matrix is defined over here. Pretty straightforward by using the Eigen C++ matrix library. That was our constructor function. This function, called compute control inputs, propagates the system dynamics and computes the control inputs by solving the model predictive control problem. What's happening inside? Over here, we extract the segment of the desired control trajectory, and let's explain this step. Our total control trajectory can look, for example, like this. Time instant k, and this is zd. For example, let us assume desired trajectory that looks like this. To implement the model predictive control algorithm, we need to extract a portion of this control trajectory. To do that, we start from certain discrete time index k, and we extract this part of the desired control trajectory, where this length is actually equal to f, and keep in mind that f is the prediction horizon, that is, this time instant is k plus f. Over here, we actually do that. When the next time step comes, that is for k plus 1, over here, we will extract this part. Let me use a different color. We will extract this part of the trajectory. And again, the length is equal to f. We extract this part, we form the lifted system matrices, we compute the solution, and we do that iteratively. So in every step, we actually extract a portion of the desired control trajectory. Next, over here, we construct the vector S. Keep in mind that the vector S is mathematically defined like this. And here is how we define this vector by using the Eigen C++ matrix library. Next, we need to compute the control input U. It is mathematically defined like this, and here's how we do that by using the Eigen C++ matrix library. Keep in mind the gain matrix is constructed in our constructor, and here's the vector S. Once we compute this control input vector, we need to extract its first block row. Again, U underline is defined like this: ukk, uk plus 1k, and until uk plus v minus 1k. We don't need these entries, we just need the first entry, and over here we extract this first entry. Once we extract this first entry, we propagate our dynamics. Here's how we do that. We compute the next state, that is xk plus 1, and the output yk, and we increment the index k, and that's it. Over here is the function that I created, and that's used to save the following variables. We save the desired control trajectory, inputs, states, outputs, and the lifted system matrices O and M. This function creates comma-separated value files that are given over here, and later on I will edit this file, that is, I will load them in Python and I will visualize the results. This function is too long and I will not explain this function in this video tutorial. That is, use it as a black box. Next, let's explain the driver code. Consequently, you need to open this file. And let's see what's happening inside. We include input-output stream, we include eigendence. Over here we include the header file and the implementation file. We're using the namespace Eigen and the namespace std. Here is the main function. We need to define all the parameters. First, we define the prediction horizon, we define the control horizon. Over here, we define the model, and keep in mind that the model is in continuous time. That is, if you go back to the tutorial, here's our model, and here's a continuous time description of the state space model. We need to define all these parameters, K1, K2, M1, and M2, as well as D1 and D2, and we need to construct the system matrices. Here's how we do that. Here's our AC matrix. AC matrix. Here's our BC matrix. BC matrix, and here's our C matrix. C matrix. Over here we extract the number of rows and columns, that is, we define M, R, and N. The next step is to discretize the state space model. We select the sampling time. The sampling time is denoted by H in the tutorial. And we define these matrices A, B, and C. We do that by using Eigen C++, and here's how we define the A matrix, and here's the mathematical description. Very easy. Next, we need to form the weighting matrices. First, we need to form the weighting matrix W3, then we need to form the weighting matrix W4. To form the W4 matrix, we do the following. We basically need to go back to the definition of W4, and we need to construct every block of this matrix on the main diagonal. Here's how we do that. In our case, the blocks are actually scalars, and I select them as 10. You can also use some other weights if you want. You can see how we do that. We simply iterate through the blocks of the matrix, and we set every block to equal to 10. Next, we need to construct W3 matrix. To construct the W3 matrix, let's look into the definition of W3 matrix. Here it is. That is, we first need to construct W1 and W2, and then we need to perform multiplication to construct the W3 matrix. Here's how we do that by using Eigen C++ matrix. We define an empty W1, we resize it, and we set its entries to 0. We define identity matrix, and over here we construct every block of W1. That is, we go block by block. Next, we construct W2 matrix. This matrix is a block diagonal matrix. Let's look into its definition. Here it is. We construct every block one step at a time. And here's how we do that. We first specify the blocks. Q0 block is a scalar, and all other blocks Q other, that is, the blocks Q1, Q2 until QV1 are denoted by Q other, and they're constant and equal to 0.001. And we construct them in this manner. And that's it. Once we do that, we define the weighting matrix W3. Here it is. And here is the implementation of that equation. Over here, we define the reference or desired trajectory. In my case, the reference or desired trajectory will look like this. K, and this is Z desired. It will be a pulse function. First we will go like this, up, stay constant for some time, for actually 100 steps, then we will go down, we'll be down for 100 steps, then we will go up, up for 100 steps, and then we will go down. And here's how we define such a pulse trajectory. Now we are ready to create the model predictive control object and to run the simulation. Over here we call the constructor. The name of the object will be MPC. We specify the system matrices, future horizon, control horizon, weighting matrices, x0, and desired trajectory. And this is the main control loop. In this control loop, we simply call this function compute control inputs for increased values of k. So k goes from 0, 1, 2 until the end. Index 1 is actually k. What is going inside? Every time we are calling this function, MPC compute control inputs. And to remind you, let's look again into this function. Here it is. What do we do over here? We extract a portion of the desired control trajectory, we compute the vector s, we compute the control input, we extract the first block row of this control input, we apply it to the system, and we increment the index. And we do that recursively on and on and on until the end of the simulation interval. And that's it. Okay, let's run the code once again. Consequently, open the driver code file, click over here and run the code. And after some time, you'll see the output over here. The output will be MPC simulation completed and data saved. Actually, we are printing this message. Okay, so that was the C++ implementation. However, we would like to visualize the result. That is, we would like to visually compare the tracking performance of our system with the ideal tracking performance. To do that, we need to open Python. In my case, I will be using Spider Editor, and actually I will open this file called Visualized Results Python. Let's open that file and let's see the results. First of all, over here, you need to select the proper folder. Let me just close this. So click over here and find the folder of your code. In my case, it's codes MPC test. Select this folder. Now, inside of this folder, you actually need to open the file called Visualize Results Python. Let's open that file and let's see what's happening over here. This Python file will actually load the data from these files: computed inputs, states, outputs, trajectory, O matrix, M matrix. That is, we will load all computed state sequences, input sequences, output sequences, as well as the lifted system matrices. Finally, let us run this file and let's see the outputs. That is, let's see the graphs. Here they are. Very nice. This graph shows two things. It shows the desired trajectory, that is our pulse, represented by red line, and it shows the control trajectory. That is, it shows the output of the controlled system. We see the following. First, the output goes rapidly up, and then we have a small overshoot, and then over here we perfectly track the reference trajectory. Then we go down, right? We are still tracking the reference trajectory. Then again, we go down, go up, and we are still tracking the reference trajectory. The tracking can be improved by eliminating these peaks over here. However, for the interest of the brevity of this video tutorial, I will not explain how to do that. Just a brief comment. You can decrease these overshoots by modifying the weights. You need to modify the weights in the driver code. That is, when you define the weighting matrix W2, over here you need to specify the weights. By decreasing these weights, you will actually eliminate these peaks, however, at the expense of the increased control input. So there is always a trade-off between the energy, that is the control energy, and the tracking performance. Still, these results are not bad, and you can even design a controller that works like this. And finally, we also plot the applied control inputs. That is, these are the computed control inputs. You see that initially they have a large value. This is because we need to rapidly go up. Then the inputs slowly go down, since you need to decrease a little bit inputs. Over here they reach a steady state for tracking this constant signal, and you can see that the pattern repeats itself. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.